The REU program gives undergraduates like me a chance to help professors with exciting research projects. This summer, I not only gained a greater understanding of aerodynamics and fluid mechanics, but I was also able to contribute some of my own research to the field. This is one of the 14 propellers on the X-57 aircraft. To simplify things, we can just look at one of the 3 blades. Since my analysis is only 2-dimensional, the blade then gets divided up into 11 cross-sections, or airfoils, to be analyzed separately. This is important because they're not all the same size. CFD stands for computational fluid dynamics. Since the math behind aerodynamics is really complicated, we often use different computer programs to plug in numbers and make lots of small calculations for us. Because of this, my research is primarily done on the computer. My main job is calculating the lift coefficient, drag coefficient, and pitching moment of each of these 11 airfoils at different angles of attack. We calculate this data primarily using a program called OpenFOAM. At its core, OpenFOAM is a C++ library that can be used for a variety of calculations dealing with pre-processing, solving, and post-processing. Here I'm running a simulation in the background to find those coefficients for a certain airfoil at a certain angle of attack. Since it will probably keep running for another 30 minutes, I'm also setting up new simulations to run once that one is complete. These new simulations deal with the same airfoil, but at different angles of attack. In aerodynamics, things are non-dimensionalized, so these coefficients represent a ratio and are unitless. As you would suspect, the lift and drag coefficients represent the lift generated by the airfoil and the drag it experiences, respectively. The pitching moment deals with the moment caused by the aerodynamic force at the aerodynamic center. Once graphed, this data will be useful in predicting stall, which is the point at which increasing your angle of attack no longer provides you any more lift. My data is used by some of the grad students I work with for more complex calculations like this. This graph shows the thrust generated at different pitches. It's kind of like the lift coefficient and angle of attack, but for the entire propeller rather than just a single airfoil. The data we calculated is shown in blue, and the data calculated by the Army is shown in green. The circles have a higher thrust than the squares because they represent the thrust at sea level where there's more density, and also because it's at a higher RPM, meaning the blades are spinning faster. We also had to run a test to make sure that our system of calculating these coefficients is reliable and accurate. We took the NACA 23012 airfoil and ran these same calculations on it. Then we compared the results calculated by OpenFOAM with the actual data obtained experimentally. Our data for the lift coefficient follows the test data pretty closely, except that we're predicting stall a little early. Our data for the drag coefficient shows that we're overestimating the drag a little bit early on, but all in all, it's not too bad.